Welcome back to ajspeller.com. In today's tutorial, we're going to revisit the related rates problem. And in this problem, we have a 13-foot ladder that's leaning against a wall. The bottom of the ladder slides away from the wall at a half a foot per second. We need to figure out how fast the top of the ladder is sliding down the wall when the foot of the ladder is 5 feet from the wall. All right, in this problem, or in this tutorial, we're going to actually use a different graphing tool to model what's going on. Analytically, we found that the top of the ladder, dy dt, is moving at the rate of negative 5/24 feet per second. All right, so before we even get into the modeling tool, let's look at the equation that we used to relate to this problem. We said that x squared plus y squared is equal to 13 squared, where 13 symbolizes the length of the ladder. All right, we want to take this implicit function and change it into a parametric equation. So here we're going to take the letter x and we're going to set the letter x equal to t. All right, now we're going to rewrite this equation, but we're going to use the t in place of the x. So this here becomes t squared plus y squared is equal to 13 squared, and now we need to solve for y. We do that by eliminating the term t squared from the left hand side by subtraction. So we have y squared is equal to 13 squared minus t squared, and we want to use the square root function to figure out what y is. So we take the square root of both sides. So at this point we have y is equal to the square root of 13 squared minus t squared. Another thing that we know from this problem is that dx dt is equal to 1/2 or half a foot per second. And we need to incorporate that half a foot per second into this problem. And we do that here with this first equation. It's implied that a 1 is sitting in front of this t. So basically, for each time unit, we're only moving 1 unit. We need to change that. For each time unit, we want to move a half a unit. So here we're going to rewrite this as x is equal to, let's pick a different color. X is equal to 1/2 t. And another way of writing that is x is equal to 0.5 t. So this here is going to be one part of our parametric equation. And now that we made that change here, we need to show this change on the y equation. So here we have the square root of 13 squared minus, and here we're going to place in 0.5 t, and that quantity is squared. So these two are going to be the two parts of the parametric equation. Another piece of information that I want to talk about is the letter t for time. We need to figure out how much time it's going to take for this particular model. And to do that, we're going to create a proportion. In that proportion, we're going to compare the feet to seconds. Here we see that the numerator 1 corresponds to foot. The denominator 2 corresponds to seconds. We want to figure out that based off the length of the ladder, which is 13 feet, so that means this numerator here is 13, how many seconds? And for seconds, we're going to use t for time. So here we just cross multiply 1 times t to give me t, and then 2 times 13 to give me 26. So here I know the t value that I need for this particular problem is going to be 26. So we're going to incorporate all this information here into our model. All right, so now let's go ahead and take a look at the model. First thing we're going to do is we're going to create some sliders. The first slider we're going to label L, and L is going to be the length of the ladder. And here we're going to say that the ladder can be as short as 1 unit and as long as 13 units. In this case, the units are feet, and we want it to increment in steps of a tenth. The next slider that we create is going to be for the rate at which the bottom of the ladder is moving, and I'm going to call that d. All right, and then with d, I want that to be limited to go from 0, and I'm going to go ahead and say 25. And let's make that also move in steps of a tenth. You know what? Let me go back up here to this one. Let's not make it 13. Let's just make it 25 so it can be variable. So, all right, so we got the ladder. We've got the rate at which the bottom of the ladder is moving. And now let's put in time. All right, the time For this problem, I'm going to set the time to go from 0 to 26 based off of what we just talked about. And I again want this to move in increments of a tenth. And next I'm going to just add in an expression to help us figure out what the time is when we decide to use this interactive model on a different problem. So to figure out the time, we take the length of the ladder and we divide it based off of the rate at which the bottom of the ladder is moving, and there we said is the letter D. So in this particular problem, well, right now it's showing 1. Let's make it work for this particular problem. We said the ladder is 13 feet, so let's set L to 13, and then the rate at which the bottom of the ladder is moving is 5/10. So let's set that to 5/10, and you see this expression gives us 26. So when you do it with a different question, once you get this part, once you set your sliders and you get the evaluation of this expression, you just come here and you change it. You change the top boundary so that it matches whatever this length here is, or whatever this number here is. All right, at this point, let's draw in what the ground would look like. So that's going to turn into a y equals problem, and notice how we have a line here showing it's horizontal along the x-axis. Well, this here is where y is equal to 0. We want to limit this to the length of the ladder, which in this case is going to go from 0 all the way to 13. So to do that, we use the curly brace here. We want to start at 0. We want it to be less than or equal to. We want that it's on the x-axis, so we're going to place the x here, and less than or equal to. We could put in 13, and notice it does show from 0 to 13. But to make this more interactive, let's use the letter L, because L signifies the length of a ladder. So let's change that to L, and we see that it still stays there. And of course, if I change my numbers here, we see that that moves here at the bottom, that blue is moving. So let's move it back to move this back to 13. All right, now let's put in the wall, and that's going to be x equals 0. Notice we have this orange line here, and we want again to limit this from 0 up to 13. Matter of fact, let's zoom out some. So right now it's going infinitely in both directions. We want to limit that. So here we're going to say we want the y values to go from 0 all the way to the length of the ladder, which is L, and we see how that's limited. All right, let's go back to the ground for a moment, and let's change the ground to green like in our other tutorials. All right, now we have the ground in place, we have the wall in place. Now let's write our parametric equation to show the movement of the bottom of the ladder. Well, to do that, we're going to put in this equation here that we calculated, where the first portion, or the first number in the ordered pair, corresponds to x. The second number corresponds to y. We're going to put in our x value. So here it's 0.5t. So I have 0.5t, and we want to keep the y value constant. And notice we are on the line here, and if I move the time, we see that it does move along that axis, but we need to be more general here so that this can be a more dynamic model. So instead of using 0.5, we're going to use the letter D, because D is what we're using to show the change in rate at the bottom of the ladder. So really it's just going to be dt, which is just d times t. And again, as we move it, we see that at most it'll stop at the 13, just like we want it to. Now let's go ahead and show the movement along the wall. Well, to show the movement along the wall, we're going to use this expression here that we have for the y value. So for the movement along the wall, the x value of the ordered pair is going to be 0, and the y value is going to be that square root. Again, I could use 13 squared, but I'm going to use L. So L squared minus, we're going to use the the x value, which is dt, and that value should be squared. And again, that's just taking what we calculated by hand here. And notice that we have this purple dot here at the top. So now when I move the time, we see that we get a simulated movement of the top of the ladder and the bottom of the ladder. All right, to make that movement a little more clear, now let's add in the actual ladder, and we're going to use the point slope equation. And the point slope equation is y minus y sub 1, is equal to the slope times x minus x sub 1. All right, in this particular problem, we're going to go ahead and we're going to use this first ordered pair here as the point. So the x value of the point is dt. So x sub 1 should be that x value, which is dt. And then the y sub 1 is 0. So here I've got y minus 0, which is just going to be y. And now I need to figure out the slope. Well, remember, the slope is the difference of the y values divided by the difference of the x values. Well, the 2 points that I'm using would be the top of the ladder, where it's sliding down, and the bottom of the ladder sliding left and right. So these two here are 2 points. So I'm going to take the difference of the y value. So here I have 0 minus this value, which is just going to be negative square root L squared minus dt squared, and then the difference of the x values, which is just going to be dt minus 0, which is just dt. And you know what? Let me put my multiplication signs in here and get rid of this letter m, and that should help us here. We don't really need the multiplication signs, but I'll go ahead and put them there to be explicit. All right, so here we have our ladder drawn in. Let's go ahead and change the style and color of the ladder. Let's make the ladder red, and let's make it dotted. And also, let's go ahead and limit the ladder. And we're going to limit the ladder using these same limits that we showed here. So let's copy that, where the x value is going to go from 0 to L. And then let's copy for the y value. And the y value is also going to go from 0 to L, where L is the length of the ladder. And then as we move, we see that we have a nice little simulation of the ladder as it's moving, as the bottom is kicking out. All right, and the last thing that we need to do is we need to show what dy dt is. So dy dt expression is just going to be the derivative of this y value here, square root of L squared minus the quantity dt squared. What we have to remember here is that the L squared and that the L and the d are constants. And what I'm going to do is just give us that part instead of actually going through that entire hand calculation. That there turns into, we have a fraction, it's going to turn into d to the second times t as our numerator. And the denominator is going to be the square root of L squared minus d times t, and that quantity is squared. Whoops, that quantity is squared. The speed at which the top of the ladder is moving down is negative infinity. So that's why that was showing as undefined. But if we move this back to where the x value was 5, and let's move it here, and let's just zoom in and make sure that we're on 5. All right, yes, we are on 5. We see that we have the negative 0.208 with 3's repeating. All right, we saw earlier that the answer to this problem was negative 5/24. So if I press enter here, actually let's do that as a division problem. So let's do negative 5 divided by 24, and we see we come out with the same answer here. And the last thing I want to show is that with this model we can actually make it animate. So I'm just going to click the play button here, and we see it animating. I want to animate in one direction, so here we see it's going to always increase. And notice that the top of the ladder is moving down at a much faster rate as time goes on, and the bottom of the ladder is moving at a constant rate. Alright, that sums up this video by ajspeller.com, and as always, thank you for watching.